Hello and welcome to iitiansgateclasses once again. We are continuing with dynamic programming today also. And today's topic, we are covering some dynamic programming algorithm. And first one is matrix chain multiplication. Okay, in your school, you must have learned how to multiply two matrices actually. But here we are given with n matrices. Okay, n matrices. And you have to multiply them in best way possible. Okay, I will tell you what it is. So basically what's happening, if we multiply two matrices, matrix A, I'm representing the matrix, first matrix as capital A, whose dimension is 2 by 3. 2 by 3 means 2 rows, 3 columns. Okay, and I want to multiply this with a matrix B, 3 by 4. Okay, you know that the number of columns in the first matrix should be same as the number of rows in the number of columns in the first matrix should be same as the number of rows in the second matrix. Only then we can multiply these two matrices, right? Okay, only then you can multiply these matrices. If you remember your school days, you cannot multiply any dimension matrices. In the first matrix, the number of column first matrix should be same as number of rows in the second matrix. Okay, because what do you do? For example, here you have something 2 by 3, right? So two rows and 3 columns. So you multiply it with this thing 3 by 4, right? 2, 3, 4, 1, 2, 3, 4, 2, 3, 4. So you pick its first row and try to multiply it with its first column, right? Like this, and you pick another row and try to multiply it with this column. So how many items are there in, you multiply this, okay, let me change the color. You multiply this row with all the columns from this, first you multiply with this one, this one, this one, and this one. Okay, so this is row 1, and you try to place row. Sometimes it is easier to place this row here vertically. So right now it's horizontal, right? You pick the row and you try to place it vertically, row 1 of this matrix, and you multiply this row, so that you cannot simply multiply. You will multiply this first element with the second element, first element of this matrix, then the second element with second element of this column, then the third element with third element this column. You add them up. Okay, and what will the and like you can say and matrix dimensions. This is like the AND matrix is C, whose dimension will be 2 by 4, right? And the effort to multiply these can be calculated as 2 by 3 by 4. Okay, so these are the efforts. Why these many efforts? So you pick the first row, multiply with every column. So how many multiplication happened here? How many multiplications? If you compare it, there are, for example, there are 4 rows, right? 4 columns. So 4 times you are multiplying 1 row. There are 2 rows. Okay, so it's 2 by 4. And how many addition you are doing after each multiplication? 3 addition. Okay, so you are adding this one, then this one, then this one after multiplication. So I'm not gonna tell you like how a matrix multiplication happens. You have to go back to school for that. But the effort is this much. Okay, let me take another example. For example, you have taken a matrix A of dimension 7 by 5, 7 rows and 5 columns. So if you are multiplying with a compatible matrix, how many rows should be there? 5, right? 5 and 2. So what is the effort? Effort to multiply these two matrices is equal to 7 by 5 by 2. Okay, if you calculate all the operations that you are doing, you are doing to multiply these two matrices, these many operations, multiplication and addition, you will do. Okay, this is the effort, total effort. This is the total effort you will do. Okay, So after calculating the efforts, what will be the end matrix? If the end matrix is C, its dimension will be 7/2. Okay, 7/2. You can take an example and try to write what will the end matrix dimension. It will be this much. Okay, so right now what you are given with three matrices. Instead of instead of having only two, you are given, for example, three matrices, and you have to multiply to them in any order possible. Right? So let's take an example of three matrices. You have to calculate D, where you are given with the matrix A 2/5 with dimension 2/5, B with 5/4, and C 4/3. Okay, so there are two order possible, right? First you will multiply AB, and the end result of this matrix will be multiplied with C. And another one is you multiply BC first, and the end result will be multiplied with A. Okay, so these are the two ways to multiply these three matrices, right? There are two ways possible. Wait a second. Right. So right now we have choices here, and once we have choices, which is the better one? So let's calculate the effort to multiply A, B, and C. Okay. Let me erase this thing, and we are going to calculate effort for both of options of matrix chain multiplication. Right. So you are given with a chain of matrices, and you have to multiply them in the same order. Like same order means you cannot simply put C here and B here, because in matrix multiplication you know that it's not commutative. Commutative means if B, you know that, okay, right? That if B multiply C is possible, it may not be true that C multiply B is possible, right? You can see here, right? The B dimension are 5/4. Okay, 5 rows and 4 columns. For that, C has to have 4 rows. Now columns are different. It's 3. Now if you try to multiply C with dimension 4/3 with B 5/4, it won't be happening, right? This is not compatible. This is not compatible. So that's why you have to apply like this order. Now, first you can either multiply BC, then the end result will be multiplied with A, and you can multiply AB first, and then end result will be multiplied with C. So it's up to you. So let's consider the effort for first thing like A, B, and C. So what is the effort to multiply AB? It's how much? 2 multiplied by 5 multiplied by 4, which is 40, right? 40. And the AND matrix will have something. If you consider AND matrix E, its dimension will be 2/4. You multiply it with C 4/3. So its effort will be 2 multiplied by 4 multiplied by 3, right? 2 multiplied by 4 multiplied by 3. How much is it? 24. So what is the total effort? Total effort is 64. Okay, 64 here. Right? So this is the total effort. Now let's consider the another one where we first multiply these two. Let's move on to the next page. So we have A with 2/4, B with sorry, not 2/4, 2/5, B 2/5, sorry, A 2/5, B 5/4, C 4/3, 4, 3. Okay. Now once we multiply these two, our effort will be 5 multiplied by 4 multiplied by 3. Okay, so it's how much? 20 and I think 60. And the AND matrix, if you consider it's E, the AND matrix dimension are 5/3. Okay, and then we have 2/5 also. Once you multiply these two, the effort are how much? It's 2, 5, and 3, and this is 30. So total effort is 90. Now you know that if you multiply AB first, then the resultant matrix will be multiplied with C. Will take how many operations? 64 operations. And here we are taking 90 operations. Now you can see that is the problem. You have to optimally multiply the matrix. Okay, so you have two orders. First you multiply AB, then C. Then another option is first you multiply BC, then A. Okay, the bracket one is saying that I am multiplying this one first. Okay, I'm multiplying these two matrices B and C. I'm multiplying first, right? After that, the end result will be multiplied. Here the effort, or you can say number of operations are equal to 90. Here number of operations 64. So obviously there is a problem now. The order of multiplication of matrix does matter. It saves a lot of time. Okay, so let's have some algorithm first without dynamic programming. Then we will introduce dynamic programming with some memory elements. That's it, right? So let's have a example here that you have A 5 by 1, B 1 by 2, C 2 by 3, D 3 by 1. Okay. Now you are given with like A, B, C, and D. How many options do you have right now? Let's try to build options. You are saying that, okay, first I will apply the brackets like B, C, D. At the end, I will multiply A, but first B, C, D will be multiplied somehow. I don't know the way right now. Okay. Another way is I will multiply AB first, then CD first. So the order of brackets does matter, right? Then I'm saying that, okay, let's do one thing. Let's multiply ABC in some order. I don't know which order. There are many options. Then I will multiply with D. And these is also have several branches like A, BC first, then D. Okay. Like BC will be multiplied first, then it will multiply with D, then it will multiply with A, right? Another option is I'll multiply CD first, right? And here also we have two options. I'll multiply AB first, then with C, then with D. Here I have another option is I will multiply BC first, then A, then D. Okay. So how many options do we have to multiply ABCD? We have 1, 2, 3, 4, and 5. We have 5 options. 5 options, right? To multiply 4 matrices. This T can be bigger tree. This T can be concluded as bigger tree, right? So now what you can do, you can try to calculate the optimal answer. You can try to calculate of the optimal answer using either by following this order or this order or this order or this order. Okay, let's do one thing. Let's solve this one so it will clear. It will be more clearer for you, right? Let's consider our matrices. We have A with 5 by 1, B 1, 2, and C 2, 3, D 3, 1. Okay, let's see our first option. A, B, C, D, and then this. Okay, and let's see how many what is the option here. Effort for BC. First we are multiplying BC, right? Effort for this one is basically how much? 1 into 2 into 3, which is 6. And AND matrix will have, if you consider AND matrix, will have dimension 1 into 3. And this 1 into 3 matrix will be multiplied with D, and effort with this one is 3. Okay, 1 into 3 will be multiplied with 3 into 1. Okay, with D. D have dimension how much? 3 into 1. Okay, so effort are equal to 1 into 3 into 1, which is 3. Okay, Then the AND matrix after multiplying all these three will be 1 into 1 only. 1 into 1 will be multiplied with A having dimension 5 into 1. Okay, these two will be multiplied and efforts are 5 into 1 into 1, which is 5. Okay, so plus 5. So how much effort do we have here? 9 plus, like this is 14. 14 in total. Okay. Now let's do the calculation for next option, which is A, B, C, D. We will multiply first. What is the effort for CD? It's 2 into 3 into 1, which is 6. And matrix dimension will be 2 into 1. It will multiply with 1 into 2 of B, which is equal to 1 into 2 into 1 equal to 4. It's not 4 into 2 equal to 2. So it will be 2. And matrix will be 1 into 1, which will multiply with A, and it will be 5. Okay. So now you can see that this option is better than this one, because our effort here are how much? Like 11 and 13. Okay. Let's erase this. Let's consider next option. Next option is third one. We will multiply AB first, then CD, then these two will be multiplied. For effort for AB will be how much? 5 into 1 into 2. Okay. You can see that it's 5 multiply 1 by 2. Okay. So if we have 5, 1 and 1, 2, what is the effort here? It's 5 into 1 into 2. Okay. So it's 10. For CD, it is how much? For CD, it's 2 into 3 into 1, which is 6. And the AND matrix for this one is 5 into 2. AND matrix for this one is 2 into 1. Now, what is the effort to multiply these two? It's 5 into 2 into 1, which is again 10. So now you can see it's 26. Okay, so this option is worst till now. Okay, so sometimes you see that they are given these bases and you just have to do the multiplication and calculate the efforts or number of operations. That's it. And you are good with the answer. Now we have A, B, C, then D. For effort for AB will be 5 into 1 into 2, which is 10, and matrix will have dimension 5 into 2. So it will be 10 plus, once we multiply with C with dimension 2 into 3, our effort will be 5 into 2 into 3. Okay. This matrix have dimension 5 into 2 and this have 2 into 3. So the total effort is 5 into 2 into 3. Okay, which is how much? 30. Okay, which is 30, right? Then the AND matrix will have dimension 5 into 3. Okay, AND matrix you can see dimension will be 5 into 3. This will multiply with 3 into 1 of D dimension. The AND matrix of this much, A, B, C will be 5 into 3, right? And if you multiply with D of dimension 3 into 1, its effort are 5 into 3 into 1, which is 15. Okay, this is huge. So we have 40, 50, 55. Okay, so let's see the last option now. Will it give us better option, better effort, or you can say less effort compared to this second one or not? So the fifth one is A, B, C, and D. Okay, so BC will give us how much effort we have already calculated. It will give 6. So you can see the dimension of B is 1 into 2. The dimension of C is 2 into 3. So our effort is 1 into 2 into 3, which is 6. Okay, and the AND matrix have dimension 1 to 3. If you multiply it with 5 into 1, our effort will be 15. 5 into 1 into 3, which is 15. And the AND matrix for this one is 5 into 3. If you multiply it with D, 3 into 1, our effort will be 15 again, right? So we have how much? 36. This is our best option. This is our best option. If we apply the braces like these, this is our best option. A, B, C, D. We multiply CD first, then the AND matrix, the resultant matrix will be multiplied with B, then the resultant matrix will be multiplied with A. This will give us 13, only 13 operation. With only 13 operation, we can multiply A, B, C, D. So this does matter, right? If you choose the wrong option, 3 times you will pay, like 55. This is huge. Okay. So now let's generalize these things, and try to calculate that we are calling one function now, MCM. How many matrices do we have? We have 4 matrices with 1 to 4. Okay, we have 4 matrices. You can say M1, M2, M3, M4. And M1 have dimension PGO multiplied by P1. M2 have dimension, you know that P1 should be there, else M1, M2 cannot be multiplied. Dimension P1, P2. P3 have dimension P2, P3. Okay, and M4 have dimension P3, P4. Okay. You know that the number of columns in M1 should be same as number of rows in M2, right? Then only M1 and M2 can be multiplied. So that's why dimension are like this. So these are the dimension, those are given, right? So we are passing first to 4 matrices, all the 4 matrices. Here, if we pass 1 to 4 matrices, how many options do we have? We have seen that. How many options do we have? I'm generalizing those. We have option like MCM of 1, 1. It means 1, 1 means we are not doing anything. We are just passing single matrix. MCM of 2 to 4. Let's consider, it's saying that this is saying we will be passing like this, M1, M2, M3, M4. We are applying braces like this. This method call indicating we are applying braces like this. Okay. Now this method will call again, right? So MCM of, you know that MCM of 2, 4 will be MCM of, there are 2 options now. Okay. So you can pass 2, 2 plus MCM of this 3, 4. Okay. Or either this one, or you can say that MCM of 2, 3 and plus MCM of 4, 4, right? You can say that, right? You can say that, right? So that's what these are saying that. Here, remember that if I'm saying that MCM of 1, 4, it means that I'm passing all the matrices M1, M2, M3, and M4. Right? I'm passing all the matrices. Now, once I say that MCM of 2, 4, it means that I'm passing all the matrices from 2 to 4, M2, M3, M4. Now, there are 2 ways to calculate it. Okay, MCM of 2, 2 plus MCM of 3, 4, right? Either this one is the way. So this is what, this is indicating like this, right? This is indicating like this. M2 will be passed separately, and we will multiply 3 and 4 first. M3 multiplied by M4. Okay, so this function call, these 2 function call are indicating like this, right? And here there is another option, which is MCM of 2, 3 plus MCM of 3, 4, 4, 4, 4, 4. Wait, sorry. So here, this, what is the mean of these 2 function call? It's mean M2, M3, then M4. This is the meaning of this one. Okay. So this is the meaning of this one. So I hope you understand. Once I write MCM, matrix chain multiplication 2, 4, we have 2 calls, and we will consider minimum of these two, minimum of these 2, right? So we are recursively drilled down to 2, 4 again. We will see minimum of these, all the options we have. Then we again call 2, 4 and try to calculate all the options we have. Okay. Okay. Now remember that MCM14 is basically minimum of all the cores, either some of these two, or you can say that MCM of 1, 2 plus MCM of 3, 4, or you say that MCM of 1, 3 plus MCM of 4, 4, right? In general, I'm writing like this. So I hope you understand. Once I write 3, 4, it means that M3 multiplied by M4. Once I write 4, 4, it means that M4 only. There's no other matrix to multiply. And what is the meaning of MCF 1, 3? M1, M2, and M3. So once I write these two like this, it means that I'm saying M1, M2, M3, M4. Now look here, the tree structure, right? So this is MCM of 1, 4, right? I'm passing all four matrices. This is MCM 11, MCM 11, MCM 11 plus MCM 2, 3, 2, 4, sorry, 2, 4. So this is the first matrices, and this is 2, 3, and 4. So that's why I'm calling like this, right? So I hope you understand how MCM means the function 1, 4 can have three options: MCM 11 plus MCM 2, 4, MCM 1, 2, first and second matrix, okay, plus MCM the 3, 4. Here, this can be written as MCM 1, 3 plus MCM 4, 4. Okay. Then again, MCM 1, 3 have two options. Either this one or this one, two options, right? Now, before going into at the more granular level, here we don't have any granular level, right? 1, 2, and 3, 4. If you look here, this is 1, 2, and 3, 4, right? There is no child branch here. There are no further options, but we have options for this one and this one. We have options again further. We have more options for this one. Before going into more options, we will calculate the effort for multiplication of these two. Right? We will calculate effort for these two. How much effort is there? Let's see what will be the dimension for the AND matrix. Once we multiply 2, 3, and 4, what will be the dimension of AND matrices? What will the dimension, right? I will give you an example here also. Once we multiply 2, 3, and 4, okay, let's check this example. 2, 3, and 4, right? 1, 2, 2, 3, and 3, 1. M2 have dimension 1, 2. I'm taking just an example. M3 have dimension. Sorry. Sorry. M4 have dimension. M4 have dimension 3, 1. Now it doesn't matter in which order do you multiply these. Either like this, M3, M4, or you multiply it like M2, M3, then M4. It doesn't matter. It doesn't really matter in which way you multiply. Both of these will give a matrix, some M dash, M indicating a matrix, the resultant matrix as M dash. Okay, and its dimension will be 1 by 1 only. 1 by 1 only. That's it. That's it. That will be its dimension. You can see that, right? M3, M4 after multiplication dimension will be 2 by 1. Right, its dimension is 1 by 2. And once you multiply these two, that AND dimension will be 1 by 1. M2, M3 dimension will be 1 by 3, and its dimension is 3 by 1. Once you multiply the AND result dimension will be 1 by 1. Okay, you can see here that this and this will give us the AND dimension. Okay, now in general, what was the dimension we considered here? P1, P2, P2, P3, P3, P4. Okay. Here we were saying that, okay, in general, each dimension is P1, P2, P2, P3, and P3, P4. So what will be the AND result dimension in general? It will be P1, P4, P1, P4, P1, P4. Okay, this will be the dimension, P1, P4. So I don't know right now what will be the best way to multiply M2, M3, and M4. I'm saying that till now, I don't know what is the best way. I just know the n dimension. N dimension after multiplying these three metrics in whichever way you are going to try it. Okay, it will be P1, P4. P1, P4 will be the n dimension for multiplying M2, M2, M3, and M4. Okay, so at last, if I multiply it with M1, M1 dimension is P0, P1. At last, for example, I multiplied M2, M3, and M4 best way possible. It gave me this matrix with M dash matrix with dimension P1, P4. And I will multiply M1 and M dash as a last operation of multiplication. So I chose this one, right? I chose M1, M2, M3, M4. Its M1 dimension is P0, P1. Its dimension is P1, P4, P1, P2, P2, P3. Its dimension is P3, P4, right? So the dimension of this end result of after multiplying this one is M dash P1, P4, right? We already concluded it, right? Its dimension is P1, P4. Let me clearly write this. So it's P1, P4, okay? P1, P4. So whatever like cost here, I don't know right now, I don't know. But I will sum that cost. For example, it's C1. I will sum up the cost, best possible optimal cost C1 with the last multiplication M1 P0 P1 multiply with M dash P1 P4. Okay, so its cost will be of multiplying M1 and M dash will be P0, P1, and P4. So this will be the cost of multiplying M1 and M dash. Okay, so it will be P0 into P1 into P4. And now I know that this cost will be there. Once I choose to multiply M1 at the end, and I choose that M1, M2, M3, M4 will be multiplied first. Okay, later on I will calculate this cost. But before that, what is my knowledge? My knowledge is this cost will be there always. If I choose the order like M1, M2, M3, M4, if I choose this order, whatever cost will be there of multiplication of M2, M3, M4, whatever cost. For example, I don't know which one is better. We have two options, right? M2, M3, M4 here, and here M2, M3, and M4. So we have two options of multiplying these two. Whichever give us the better result, its cost will be considered as C1. But I know that this cost of multiplication of these two matrices, this one and this one, will be P0, P1, P4. P0 multiplied with P1 multiplied with P4. This will be the cost. It's always will be there, right? So here, what I can say that there is a cost associated of this split. This you can say this choice, which I already know. It's P0, P1, P4. Okay, it will always be there. And for this one, what is the cost? Similarly, let's calculate for this one first. Okay, what will be the AND matrix for 1 to 3 for this one? It will be P0, P3. After multiplying 1, 2, 3 in any order, in any like best order or any possible order, the AND matrix will be P0 multiplied with P3. Here, the matrix have the dimension P3, P4. So I know that once I have the cost for this one, I multiply this with M4 and I have a fixed cost here, P0, P3, P4. This won't go anywhere. This will remain here. If I choose this way, if I choose to split the matrices, matrix multiplication this way, this cost will be always be there, right? Similarly, for this option, what will be the AND matrix? It will be P0, P2. What will be the AND matrix for this one? P2, P4. So what will be the cost here? P0, P2, P4. Okay. So this is the way to split 1 to 4 if we have given 4 options. What if we have given 100 of the matrix? Okay, so what we can do, let's consider one more variable, like this thing as I, this thing as J, and let's define if I can be anything, J can be anything, just that I has to be greater than, less than equal to J, right? This is the only possible. We cannot cite like MC, M4, 2. It does not make any sense, right? We are saying that okay, it can be 2, 4. So it's I, it's J. I should be less than equal to J, right? That's it. Now let's move on to more generic definition. MCMIJ. What can we say by seeing this result? MCM14. Okay, let's try to write it more clear way. It's a bit messy. Then only we can see the results. Like MCM1, 4. So we know the dimension M1 have P0, P1, P0 by P1, M2 have P1 by P2, M3 have P2 by P3, M4 have P3 by P4. Okay, these are the dimensions. And I'm saying that we have following choices. We have first choice as M1, M2, M3, M4. I am indicating this choice as MCM1, 1 plus MCM 2, 4, and there is a fixed cost to it, P0 and P4, P1 and P4. Okay, and there is another choice is like this choice in term of function can be written like this, right? Like this. Now another choice is M1, M2, M3, M4. This choice can be written like this: MCM 1, 2 plus MCM 2, 3. MCM 3, 4. And we know that once we multiply these two, it will give us the cost as P0, P2, P4. Okay. Then we have one more choice, which is M1, M2, M3, and at the end we will multiply with M4. This can be written in function format as MCM 1, 3. Okay, 1, 3 plus MCM 4, 4 plus the cost related to is P0, P3, P4. Okay, right. Let me highlight with red color also. So this is the first option in case of function we are saying. This is the second option in case of function. This is the third option. Right? So these many options we have right now. Okay. And these are the calls roughly in form of brackets I have indicated, right? And you can check it here also. I have highlighted here. In the next 3 slides, I have explained the function calls. Okay, so what we can say after looking to this matrix, M1 is M1 cost we can indicate as P0, P1. M2 cost is indicated as P1, P2, right? This number is 1 less than this matrix number. So for MI, we can write it like the cost, not cost, dimensions. The dimension can be written as Pi minus 1 multiplied by Pi, right? If I consider ith matrix, its dimensions are written like Pi minus 1 Pi, Pi minus 1 Pi, okay? You can see here, like M3 is written like P2, P3, right? So its dimensions are written like Pi minus 1 Pi, okay? Now let's try to write it in generic format. So MCM Ij can be written as these many functions calls we have. We will write it like MCM II, right? Plus MCM I plus 1 J plus dash dash dash. Okay. Here we write the MCM I comma I plus 1 plus MCM I plus 2 comma J plus this is some cost, like you know that here we write some generic like Pi minus 1 Pj and sorry, let me try to write the dimension of these matrices. This matrix dimension is Pi minus 1 Pi. Okay, this matrix dimension is Pi Pj plus 1, not Pj plus 1, sorry, Pj only, because the last matrix here is Mj, and Mj dimension is Mj minus 1 Mj, sorry, Pj minus 1 Pj. Okay, here the matrix is Mi. Matrix is Mi only. There is only one matrix, right? So if you multiply these two matrices and resultant matrices, our dimension will be, our cost will be Pi minus 1 Pi Pj. Okay, it's Pi minus 1 Pi and Pj. Okay, and here the matrix is matrix dimension, the end result matrix dimension is Pi minus 1 multiplied by Pi plus 1. Here the matrix dimension is Pi plus 1 multiplied by Pj. So here you can calculate the cost of multiplication of these two resultant matrices with this cost is Pi minus 1, Pi plus 1 and Pj, right? And similarly, if you follow back the previous order here, this is I, this is I, this is I plus 1, this is J, this is I plus 1, I plus 2 J, I, and this is I plus 3 J, right? So here if you can, in generic I'm writing, so you can follow up like this. So the last function call will look like MCM I comma J minus 1 plus MCM J, okay, JJ. This is actually I minus, sorry, J minus 1, yeah, this is J minus 1. This is JJ. So the resultant matrix of this one is, the resultant matrix of this one is how much? What will be the resultant matrix dimension? Pi minus 1, Pj minus 1. Resultant matrix of here is Pj minus 1, Pj. So the operational cost of multiplying these two matrix dimension will be Pi minus 1 plus Pj minus 1 plus, multiply by Pj minus 1 multiply by Pj. Now try to look here that Pi minus 1 and Pj are fixed. Just this I plus 1 is changing. I plus 1 is changing. See, right now it's I, then it's I plus 1, then it's J minus 1, right? So this will increase. It will increase from I plus 1, I plus 2, I plus 3, I plus 4 till J minus 1. So we are going from I to J, and we can give it a variable like some X, and try to write all these call in format of X. So this X will vary from I to J minus 1, I to J minus C. It's varying from it's I here, I plus 1 here, then it's I plus 1 here, I plus 2 here. In next call it will be I plus 2, I plus 3 till J minus 1 and J. Okay. So this X will vary from I to J minus 1. Let me try to write it in more generic format. MCM I J. Okay, where X is varying from I to j minus 1. So you can write it like MCM I comma x plus MCM x plus 1 comma j. Okay. So it will vary from this thing. This is the thing, right? And here the cost will also be pi minus 1, px, and tj. Once you try to vary this x from I to j minus 1, you can generate all these calls. You can generate all these calls. Okay, all these options. Now we are, instead of considering ij, we have considered a variable x. Okay, so this is the generic format of calling MCM. Okay, so how many distinct MCM calls do we have? How many distinct MCM calls do we have? Distinct. If we consider like 1, 4, we have 1, 1, we have 1, 2, 1, 3, 1, 4, we have like 2, 3, 2, 2, 2, 4, and we have 3, 3, and 3, 4, and we also have 4, 4. So these many distinct calls we have. These many distinct calls we have. Right. So if we have n matrices, here number of matrices are 4. We can have at max like these many calls. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 calls we can have. So in general, you can say that for a given value of n, we can have n square. N square I'm considering as worst case scenario. N square calls. So if you use dynamic programming, we can save these into a memory. Number of, you know that using previous lecture that the number of calls the result of this call can be saved in a space. From there we can refer and we don't have to solve it. Okay. So that's why the number of calls are there. This number of calls are important. So we have n square maximum calls. So what is the time complexity? It's order of n square, right? No, it's not. It's order of n cube actually. You have n square calls and effort of calculating the minimum out of all the calls. For example, here, this is not the answer. Actually, it's minimum. If you have n distinct call for this one, like n distinct call for this one, and distinct call for this one, right? You'll calculate minimum of these things, right? So that is why it's actually order of n cube. Dynamic programming says that the number of distinct calls can be saved. Its result, distinct call result, can be saved in a memory. So we don't have to solve it. This distinct call can be like a subproblem calls. In the previous lecture, I already explained that we save these distinct calls in memory. So we will never call that function again and that function call the subproblem and subproblem. So we prune that tree, and the pruning of this this tree. So if we solve some problem here, we don't have to call the same parameters having the same matrix multiplication here. We don't have to call it. Let me indicate it here in the tree. So if you see here, right, this CD is getting multiplied here. This CD is getting multiplied here. So once you solve the CD multiplication here, you don't solve it here. You will never solve it here, right? Okay. For example, this BC getting multiplied is also getting multiplied here. So once you solve the BC multiplication and you save it in a memory, okay, the multiplication of BC having value 16 or something, I don't know. Like I'm just giving an example. It's 16. Then I will say that, okay, here it's 16 also. So the solving of this again will be saved. So that is how we are saying that there are total n square distilled calls. Like you can start the number, we have n matrices, you can start from 0. So how many possible distilled calls are there? Like 0 to n, we have numbers, right? 0 to n. So we can have 0, 1, 0, 2, 0, 3, 0, 4 till 0 n. N number we have here. Similarly, like we have 1, 1, 1, 2, 1, 3, 1, 4, 1 n. We have n number here. Okay, n minus 1 number here. Here we have n number. And you add these function calls n plus, n minus 1 plus, n minus 2, like this. You have n order of n square calls. And each call we are taking order of n because out of these calls, you have to find the minimum. And finding the minimum in n numbers will take order of n time. Finding the minimum in n number will take order of n time. We don't have to construct a min heap. If you construct a min heap, it will again take order of n only, right? So it's finding out the minimum out of these calls will take order of n time. And we have order of n square calls. So we have n square multiplied by n. Order of n cube is the time complexity of matrix chain multiplication. What if we don't use dynamic programming? So we have a tree-like structure here. Okay. At the worst case, we will consider we have like in case of 4 nodes, 4 matrices, 4 matrices. We have already seen that how many calls are we making? In case of 4 matrices, we are making 3 children, and these 3 children are making at least 2 calls. This is not making anything, but in worst case, you can consider we are making 2 calls. So here we have n minus 1. Here we have how many calls? N minus 1 are making n minus 1 multiplied by, you can say, n minus 2 calls, right? Then again, this will make 1 call, 1 call, 1 call, 1 call, 1 call. How many calls are there? It's n minus 1 into n minus 2 into n minus 3 calls. So in total, we have factorial n, or you can indicate like factorial n calls. Factorial n time complexity is basically n raised to power n. So without dynamic programming, let me try to write it here in clear manner. Without dynamic programming, matrix chain multiplication will take order of n, and this is very large, very large, very large. Okay. With the dynamic programming, it will take order of n cube. Okay. So that's it for today, students. Thank you all for joining.